A warm welcome to the YouTube channel Video Wissen. Today with a very special feature. We are celebrating XMM-Newton 25 years in space. It was launched on the 10th of December 1999. And we take the opportunity to introduce you to the mission itself, to the observatory, and then we are highlighting a few of the aspects that we here in Potsdam have been doing scientifically using XMM-Newton to answer scientific questions that are of interest to us. Enjoy it! Die deutsche Version unserer Beiträge finden Sie auf dem YouTube-Kanal Urknall, Weltall und das Leben. Viel Vergnügen!
Hello, also from me a welcome to a special edition on Video Wissen on occasion of the 20th anniversary of XMM-Newton and to a journey to hot processes and exotic objects in our universe. My name is Iris Traulsen, I'm a postdoc at the AIP and I work for the XMM-Newton Service Science Center, which is kind of a service team for science with the XMM-Newton telescopes. Here you can see an artistic view of the XMM-Newton telescope, better the XMM-Newton mission, with 3 X-ray telescopes in the front and a bit hidden next to them also an optical and UV telescope on a space-based satellite. Space-based because Earth atmosphere relatively effectively shields the X-ray radiation from the universe. So if we want to evaluate it scientifically, then we have to put our telescopes in space. XMM-Newton orbits Earth in about 48 hours and the project is closest at a few thousand kilometers and the farthest point away from Earth is more than 100,000 kilometers away from us. XMM-Newton observations have to be proposed, which means that scientists who would like to get XMM-Newton data have to justify the scientific value and to explain how much time they need to an evaluation committee, and in the end about 1/7 of this proposal can be granted and observed, because although XMM-Newton observes more or less all the time per year, there's only time for about 1/7 of these proposed observations. And this results in this pattern of observations that you can see here in a sky map, which is similarly designed as a map of the Earth. And each colored dot in this map means a XMM-Newton observation since its launch. And the brighter the dots, the longer the accumulated observation time in this sky patch. And the observation time collected so far ranges between about 15 minutes and more than a month collected over the years in a certain sky patch. Meanwhile, as of today, XMM-Newton has orbited Earth more than 4,500 times. It has collected 16,000 observations, which contain several hundred of X-ray sources in the universe, which are hot stars, galaxies, other objects that you hear more about in this series of short talks today. And as a usual measure of scientific output, we use the number of articles published in journals, and we have collected several thousand so far dedicated to XMM-Newton observations and the analysis of their data. XMM-Newton carries X-ray CCD detectors behind its telescopes, and they have the specialty that we can obtain several kinds of data products with just one observations. From the data we get, we can create images, which you can see to the left. In the center of this image, there's a bright binary star. We measure the brightness of our objects and its evolution with time, which we call a light curve. And in the middle panels, this is shown in different energy bands of XMM-Newton for the same binary star from the image to the left. And we split the light into its colors. We measure how much X-ray photons we receive at which X-ray energy, which we call a spectrum, and from that we can learn, for example, about the chemical composition of our targets. Why are we so interested in X-ray observations that we bothered to build X-ray satellites and send them to space, because we measure processes that we cannot observe directly on Earth. We go into the hot and extreme universe, illustrated here by ESA on several examples ranging from active stars over clusters of galaxies surrounded by hot gas up to large-scale cosmological structures. And today several colleagues of our institute will give you examples of our work with XMM-Newton data and which knowledge we can gain from this instrument. So we welcome you to a journey to stars made from exotic matter, to hungry black holes, to grilled exoplanets, surprising light flashes, and many more features. Have fun!
Hello, my name is Mirko Krumpe, and I would like to introduce to you the fascinating research field of fast radio bursts. This field is relatively young, and it deals with extremely bright radio output in the universe that only lasts for milliseconds. The Parkes radio telescope, which you can see on the right side, has already recorded these events in 2001, but they were only discovered in 2006 and then published in 2007. But what is known about these radio bursts? From our measurements, we know that there have to be of the order of 10,000 of such events per day on the whole sky. The luminosities of these things can go up to 10 to the 35 watts. In this figure here, you see a few events. So in this upper panel here, you can see that first the radio flux is pretty much zero, and then suddenly you see these bursts. And in this image, you can see on the x-axis the time, and here the radio frequency, and you can also identify these events. From the duration of these events, we can infer the size of the emitting region. And this is really astonishing. The size where an energy is released that is 1 billion times higher than what our sun is producing is coming from only 200 meters up to 1.2 kilometers. We know that most of these events are extragalactic sources, and we also know that there are two types. There are the objects that only show once such a dramatic radio emission and then never again. And then there are other objects that show repeating fast radio bursts. The time between these radio bursts can be very different, from milliseconds to hours, maybe even days. And at some point they disappear. Why all that happens is completely unknown. Currently, it's really favored that this is somehow related to neutron stars with extremely strong magnetic fields. Just to remind you, a neutron star is an object that has roughly 20 kilometers in diameter and has a mass of roughly 1.2 to 2.4 solar masses. But why are we interested in observing these things in X-rays? There are currently of the order of 100 different theories that try to explain what these fast radio bursts are. And these different models make different predictions in the X-ray what we will observe. So far, only one case is known. You can see the plot here, where in an object we could see at the same time radio bursts and X-ray bursts. Why is there only one object? Well, it's very complicated to coordinate simultaneous radio and X-ray observations. You have to imagine that the radio telescopes are ground-based and they cannot observe the entire sky the whole time. And for X-ray observation, we have to go in space. So for this, we have to request observing time on big satellites. And this is also very difficult to achieve. So we nevertheless established now an X-ray observing program with XMM-Newton for these fast radio bursts. And here again, we split on these two kinds of objects. There are the once-off fast radio bursts, and for these objects, we just look at the schedule when XMM will observe which part of the sky. And during these times, we try to also go there with big radio telescopes. If we now discover in the radio data that there was a fast radio burst, then we go back to the X-ray data and try to analyze what happened there. The problem here is that we have to do this for 80 hours to find one single object. So this is really difficult. For the fast radio burst repeater, we follow a different strategy. These objects are rare, and so radio telescopes observe these objects anyhow to analyze how often these peaks occur and what's the time difference between them. When we know about such an object, then we request to put XMM on this object and to find out if there are X-ray emissions at the same time. Unfortunately, I cannot show you results yet because we just initiated this project and are still collecting data.
Hello, I'm Katja Poppenheger. I'm a professor and director here at the AIP, and I work a lot with X-ray photons from the XMM-Newton telescope. I work on exoplanets. Exoplanets are planets that are not inside our own solar system, but that orbit other stars outside our own solar system. And those systems can actually look quite different from what we are used to from our own solar system. So what you see here is a little depiction of what we know from home, so to say. We have the rocky planets in the closer orbits around our own sun, and we have the gas giant planets, Jupiter, Saturn, and so on, in the farther orbits. Now, in some exoplanetary systems, the whole situation can look quite different. This is a depiction of the 51 Pegasus system. This is the first exoplanet that was discovered around a star that is similar to our own sun. And this planet here is roughly Jupiter-sized, but it orbits its host star within just a few days, so much, much closer than even Mercury that is in our own solar system. And this has the consequence that this planet here, 51 Pegasus b, is very hot. It's a so-called hot Jupiter. And that becomes very important also when we look towards X-rays that we study with XMM-Newton. Because what happens with such hot planets, and especially with hot gas giant planets, is the following. What you're seeing here is basically the black circle. That's the radius of the exoplanet as we see it in the regular optical, in the visual light. Now, these planets have an atmosphere, and the X-rays are absorbed high up in this atmosphere. So X-rays come from the central star, get absorbed high up, and it's actually the same situation here for ourselves on Earth. This is the reason why we need to do X-ray astronomy from space, because also here the X-rays from the sun get absorbed high up in the atmosphere and they don't actually reach the ground. Now, what happens with the atmosphere of such a planet? We have all those X-rays that are being absorbed up here, and then the atmosphere heats up and expands. And if this effect is strong enough, what can happen is that the atmosphere expands so much that it goes beyond the gravitational well of the exoplanet. So it's not bound to the planet anymore, and it drifts away, which means that our atmosphere is slowly getting lost over time, and it can even be so extreme that the whole atmosphere evaporates over hundreds of millions of years for these exoplanets. Now, with XMM-Newton, we can study the X-rays that come from the central stars, and here is one such observation that I did some years ago with XMM-Newton. This is the Andromedae system. What you can see here with a big arrow pointing at it is the star that hosts these exoplanets here. And what you see also in the image, it's a false color image of X-ray colors. You see that this star is quite yellow in color, which shall depict that it is a relatively soft X-ray source, kind of like our own sun actually. And now I want to show you some of my favorite star exoplanet systems. So there's the Andromedae one on the left that you just saw in a little bit bigger. It's a multi-planet system actually, and also has another star in the system, which makes it quite interesting for people like me who like to study stars and planets. In the middle, we have the HD 189733 system. And this is a system that a lot of people worldwide like to study a lot because it has an exoplanet that produces a so-called transit. So the planet goes around the star exactly in our line of sight so that the light from the star shines through the atmosphere. And so we can learn lots of things about what the atmosphere of that planet is doing. And then on the right-hand side is a really, really popular system, and one that I also like a lot. That is Proxima Centauri. That is our nearest neighbor star, and it actually is orbited by a so-called temperate planet. So it's a small planet that is in the temperate zone, which means that the surface temperature of that planet is such that in principle liquid water could exist there. We don't know yet if there really is water or if there is an atmosphere at all, so there's still very much to learn about this and also the other exoplanet systems. But that's of course what makes life exciting, and there's much work to be done. I'm looking forward to more XMM-Newton data, and this is what I wanted to tell you about my research.
Hello, my name is Axel Schwope. I am happy to coordinate the work of the X-ray astronomy group here at the Leibniz Institute for Astrophysics Potsdam since many years. And since 1997 we are really active in the XMM-Newton Survey Science Center, and after the launch of XMM-Newton we were able also to do X-ray observations for scientific investigations. And there's one aspect that I would like to highlight today in my contribution on compact binaries. So what's that? Fasten your seatbelts, put your X-ray goggles on, and then let's go to space and let's perform an observation with XMM-Newton. And here we go. What you are seeing, that are two movies at the same time, reflecting the same or showing you the same X-ray data. On the left-hand side, as the photons, the photon rain is incoming at the very moment. On the right-hand side, you see the integrated signal that we are getting by collecting all the photons on our detector. And what you immediately see is that many of the other objects in the field of view, they are more or less constant, if you're able to spot this. But the one object that is here circled in white light, with a white circle, that is very strongly variable. And that is now here shown on a very compressed time scale. The whole observation took more than 7 hours, and we show it here in just 30 seconds. But you see that as you observe the X-ray sky, a lot of things may happen. So what has happened? What kind of object we have observed here? It's a compact binary, where a star, which is similar to our own sun, this red guy here, which is much smaller than our own sun, has just 20% of the radius of our sun, loses matter to a compact object, which is even an object which is even much smaller. A so-called white dwarf has the size of our own Earth. And while the matter is streaming, it's catched by strong magnetic fields and then guided down to the polar regions. So what's happening there? There is where the action is, which we can observe in X-rays. The energy that is brought along with the matter, which is carried by the matter, is there, released and eventually radiated into the space as an X-ray signal. And the plasma there might be as hot as 200 million Kelvin. And we were interested very much to get more information about those phenomena, about those objects. And XMM-Newton was the ideal instrument to use to exactly perform such observations. So we were selecting an object that has a special geometry. And the special geometry is such that the two stars, for us, apparently rotate in the same plane, which means that the star which gives away the matter, is from time to time casting a shadow on the white dwarf star. And that means by observing the time variable signal, we can learn about the size of the white dwarf, or on the accretion region on the white dwarf, and on the temperature and things like that. And that's what we were investigating with XMM-Newton. Here you see the red star as it is at one position, obscuring the white dwarf which you see in the back, and the small spot on it, that is where we expect the X-ray activity going on. So we were choosing the best target, namely the brightest of those objects. We were choosing the best telescopes for that, namely XMM-Newton on the X-ray side, and we were able also to combine it with the large telescope, with a very large telescope in Chile, so that they were observing at the same time the target for 5 hours back in May 2005. And after all, when we got the data, we saw this. That was quite a disappointment. Namely, there were just a handful of X-ray photons that we could collect from our target. It may happen from time to time that the stream of mass transfer of the one star to the other is ceased, for whatsoever reason, so that we are no longer seeing the white dwarf and all the action going on there in the X-ray. We are seeing some radiation from the mass-losing star and some optical radiation, in principle, from the white dwarf. So the observation that we have been doing was not completely useless, because XMM-Newton has not only the X-ray telescopes on it, but it also carries an optical monitor. That is that little thing here that is also observing the same direction as the X-ray telescopes. Here the telescope is in the laboratory. It's just a 30 centimeter telescope. quite small, but located in space, you are no longer in your observations hampered by atmospheric scintillation and atmospheric absorption. So you could observe even in the ultraviolet. And that's what we were doing. Here you see the light curve of our target. And that shows the deep eclipse, now in ultraviolet light, observed with the optical monitor. And then you see this light change. So what are we seeing here is indeed a very large spot, which gives rise to the smooth variation. And by modeling such an extended warm or hot spot, we could even reflect our observed data quite well, at least, as far as we could say. And the size of the spot that we had been modeling here is of the order of, say, the North American continent compared to the size of Earth, which is the size of the white dwarf star. But we were still interested to get the X-ray signal, to learn about the X-ray radiation from such a process. This time, 8 years later, in 2013, we did it better. We were even better prepared. We used our IEP-owned telescope, Stella, which is located on Tenerife, observing it every second night, checking if our star would be bright and continuously bright. And when we were convinced, yes, it's continuously bright, then we sent a trigger to XMM-Newton, please observe now. And that was then happening. This is our X-ray light curve that we observed from our target star when we triggered the XMM-Newton observations in a high state. And what we are getting is really a marvelous signal. So we were covering 5 orbital cycles of this binary consecutively. And this is indicated here by the numbers along the x-axis. One orbital phase is of this binary of 125 minutes, so we were observing for more than 10 hours consecutively. And along the y-axis is shown the X-ray signals, the rate, the number of photons that were arriving in the detectors per second. It goes up to 100. Marvelous signal. And every 125 minutes, there's this X-ray eclipse. On the next slide, we take a detailed view in the average light curve. So putting all data on top of each other, we see that the X-ray light is completely obscured for of order 10 minutes. Every 125 minutes. And from the time it takes for the object to completely extinct, so to say, the X-ray signal and then reappear after a while, we could derive the size of the X-ray region on the white dwarf, which in this case is less than 2 seconds, which translates into a linear dimension of about 1,000 kilometers. So putting it in perspective, that's the size of Germany or the size of Earth, which is the size of our white dwarf star. So this is just one of the aspects that we were able to derive from such XMM-Newton observations as compact binaries, and you see the action while you're observing, and that's one thing that I really wanted to bring you to your attention. Many thanks.
Hello, I'm Virginia Cuneo. I'm a postdoc at the AIP. I started working here a few months ago, and today I'm going to talk to you about characterizing cataclysmic variables using XMM-Newton. So cataclysmic variables are binary systems in which one of the components is a compact object, but it's not any compact object. It is particularly a white dwarf. So due to the proximity of the 2 stars in this system, there's mass transfer from the companion star, in this sketch is the normal star, onto the white dwarf. And we can classify mainly the systems between magnetic, which include polars and intermediate polars, and this is in the case where the white dwarf has a magnetic field, and non-magnetic systems in which we have the dwarf novae and the nova lights. So in our galaxy, it's been estimated that there are approximately 10,000 cataclysmic variable candidates. However, most of these sources are found in surveys that include many other objects, not necessarily only cataclysmic variables. Particularly, Rosita, there is an X-ray telescope that surveys the sky 4 times, has recently discovered a big sample of cataclysmic variable candidates. And with later observations, we were able to confirm these cataclysmic variables by using different techniques and different telescopes, particularly by obtaining a spectroscopy in the optical spectral range. Despite confirming these cataclysmic variables, we still don't know what type of cataclysmic variable they are. And here is where XMM-Newton comes in, playing a key role. So to determine the nature of the cataclysmic variable, we need to analyze the variability of the system. And this variability is mainly studied in X-rays because at other wavelengths, some types of variabilities are very hard to observe. So the big amount of photons that XMM-Newton is able to collect allow us to perform detailed studies of individual systems. And here I show you an example. So on the right, we have a light curve of one of these systems that was discovered with the Rosita. And this is a light curve that we obtained with XMM-Newton. The light curve is basically the brightness of the system along time. So we can see how this varies. And applying different techniques, we can determine the periodicities in this system. What we are looking for is, for example, the orbital period, that is the time that it takes the two stars to complete a full orbit, or the spin period, that is the time it takes the white dwarf to spin once. And these periodicities give us a lot of information on the nature of the system. So, for example, if we observe a spin period, we know for sure that we are in the presence of an intermediate polar cataclysmic variable. On the other hand, if we don't observe or don't determine any periodicities apart from the orbital period, this suggests that the system is non-magnetic. Classifying the X-ray sources in the galaxy is crucial for determining the galactic population of compact objects and advancing on our understanding of stellar evolution. And XMM-Newton undoubtedly plays an essential role in this mission.
Hi, I'm David Homan. I work at the AIP as a postdoc, working with X-ray data and specifically looking at extragalactic sources, which is what I want to talk to you about today. In the image here, you can see an X-ray image, a very long exposure X-ray image of a field that's far outside our Milky Way. So there's no foreground sources, there's no stars or anything else that's close by in our own galaxy. These are all sources that are very far away. These are other galaxies at millions to billions of light years away. So in the image, you can see some larger spots. These are galaxy clusters, and you can see lots of individual points. These point sources are all individual galaxies. And because we are looking at an X-ray image, that means that something very energetic is happening in all these galaxies. So the question is, what is that? So if we look at a close-by example, this is NGC 1365, you can see the light from all the stars. This is all optical light. So you can see the stars, you can see the gas, and you can also see that the center is much, much brighter than the rest. And what is in the center is what's referred to as an active galactic nucleus. So AGN for short. This is the term that we often use for it. If we take a closer look at the center, specifically in the X-ray, so this is again an XMM-Newton image, you can see the core is very, very bright. So we can see some other objects in the galaxies, but the nucleus is much, much brighter. That is where all this X-ray energy is coming from. And the origin of this X-ray, so this is just an artist's impression, of course, this is not a real image, but the X-rays are formed around a supermassive black hole. So these are black holes that are much, much heavier, more massive than our sun, up to a million to a billion times more massive. They attract matter from their surroundings, which heats up to very high temperatures and start to emit X-rays. And that is what we see. And these are the objects that I study. If you look at the image on the left, you can see that we have a pretty reasonable idea of the spatial distribution of these objects. We can see where they are in space, but the new frontier in research is to look at how they develop in time. Essentially, we're adding this extra dimension and investigate how they evolve. And this is my main topic of research. So how do we do that? In our particular project, we make use of data from another X-ray satellite called eROSITA. eROSITA scanned the X-ray sky, so the full sky, every 6 months. So there are repeated observations, which means that we can see the same object first at the start, then 6 months later, then another 6 months later, and we can track it over time. And this is what you can see on the right. So this is a cutout, a very small cutout where we can see one individual galaxy. You can see at the start, at 0 months, there's nothing there, and then suddenly there's a bright emission. So that means that within those 6 months, a lot of energy is suddenly being produced in that source. And these are the objects that we are looking for. So starting with the eROSITA data, we pick out objects that do something like this, that evolve very spectacularly, and then we dedicate a lot of follow-up observations to it. So we track these objects in a more dedicated form. We try to get observations across the electromagnetic spectrum. So from the infrared, where we have data from the WISE satellite, for example, in the optical, where we use terrestrial Earth-based telescopes, specifically in the southern hemisphere in our case. And in the high energy, which is of course of particular interest here, we use XMM-Newton to track how these objects evolve over time. And XMM is most suited to this particular project, specifically because we can now dedicate time to observe individual objects. It's not scanning the full sky. We can point it at the object, get a long exposure on this single object. We can do this several times to, again, track how the object evolves. And we can get an X-ray spectrum. In other words, we can get an idea of how the energy in the X-rays is distributed. So whether or not it's emitting more energy at high wavelengths or at short wavelengths, essentially. What does this actually look like in practice? So this is from the same object that we saw the flashing image of before. So at the top left, you can see an XMM-Newton image. So we can see we took a long exposure of it, and you can see this very, very bright source. So when we observed it, it was still in this really, really bright state. Now in the optical image, which is below it, you can see that it's associated with one particular galaxy. So it's part of a small group. You can see 3 smaller galaxies to the south of it, but it's the northern galaxy where this event happened. Now in the middle, in the bottom, you can see the optical light curve. So this is optical light from just a telescope or a group of telescopes on Earth. You can see that it was at a relatively low level. So on the y-axis is the brightness, on the horizontal axis is time. I can see that suddenly there's this large outburst, which was coincident with the X-ray emission. So at the same time as this large outburst in the X-rays happened, this large outburst in optical light happened as well. There's a lot of brightening happening at the same time. Now, what we were able to observe with XMM is that even on much, much shorter timescales, so if you look at the plot above in the middle, so the blue dots, this is, in total, this spans several hours. This is one full XMM observation. Within that time, the brightness already changed by a factor 2 or so. So even on these very short timescales, the energy output changes massively and very dramatically. What we're able to detect is not only that this object is really variable, but because we now have a really good X-ray spectrum, we were also able to get an idea of what is actually causing the emission. In this case, the emission comes from very hot gas, around 1 million Kelvin, which is about 1 million degrees. And this gas is heated by rapid inflow into the black hole. Essentially, the friction of the gas heats it up. And for something that quickly to happen, the most likely scenario, we think, is a case where a star passes relatively close to the supermassive black hole. So there's already material there. There's already some level of activity, but a star gets mixed in the other gas and gets torn apart by the gravitational shear of the black hole. And suddenly there's a lot of extra material that becomes free, starts to spin in. So this is, again, an artist's impression that you see here, of course. And this gas falls into the black hole very, very rapidly, heating up and starting to emit all these X-rays and this other optical light, and starts to dim slowly in the months and years that follow. And we have been tracking that as well, which is still ongoing. Well, these are the kinds of objects that we look at. This was just one example. We have many more, but this is the science that I wanted to talk to you about today.
Hello, my name is Nicoleta Ilic. I'm a postdoc at the AIP, and I'm going to tell you something about the stellar corona. The stellar corona is the uppermost part of the stellar atmosphere. It has a very low density and a very high temperature. Depending on the spectral type, its temperature can range from 1 to 10 million kelvins. Here in the picture, we see the solar corona in optical wavelengths, and this is only observable during a solar eclipse. Here we see that the coronal plasma follows the magnetic field lines of the Sun, and around the equator we have this complex structure around active regions. Now, if we change from the optical part of the spectrum to the UV and X-ray part, we can see the coronal structure much clearly. Again, there is plasma following the magnetic field lines of the Sun around the bright features, which are also the active regions of the corona. These are typically very hot, while the darker regions of the corona are typically cooler and less active. Of course, these kind of features of the solar corona are only observable because the Sun is very close to our instruments, and we also are able to send telescope in orbit around the Sun, so we are able to have these nice observations. However, if we go to the stars, which are point sources on the sky, then when we observe them with X-ray telescopes, they also appear as point sources in the detector. Here we see an observation of the binary system GJ15, which is taken with the EPIC PN instrument on board XMM-Newton. Here the two stars also appear as point sources. With this particular instrument, we are able to measure the position of the detected photons, their arrival time, and also their energy. What we actually are interested in is the flux of the X-ray photons we measure, and if we know the distance to the stars, we are also able to measure their X-ray luminosity. Now, if we have a particularly bright star that emits large amount of X-ray photons, then we are also able to plot X-ray light curves, which we can see here. On the x-axis we have the observation time, and on the y-axis we have the number of photons per time bin. Here we see that during the observation the star GJ15A experienced a flare, which increased its X-ray flux and made it appear brighter than its stellar companion, although these two stars have the same age, same spectral type, and have the same distance, so they should not actually differ that much, but because of this flaring event, we have that one star appears brighter than the other. So now you might ask, why is it actually interesting or important to be able to measure the X-ray luminosity of stars? Well, studies have shown that the X-ray luminosity of main sequence stars depends on the stellar age and the stellar rotation period. Here in both diagrams, on the y-axis we have the X-ray luminosity of stars, and on the left-hand side on the y-axis we have the rotation period. On the right-hand side on the x-axis we have the age. And in both cases we see that the X-ray luminosity of star decreases with increasing rotation period and increasing age. So, if we are able to measure the X-ray luminosity of a particular star, at the same time, if assuming that it is a main sequence star that follows these relations, we will be able to estimate its approximate rotation period and its approximate age, which are parameters that are typically very difficult to determine. So, because of this, we are very happy that we have an instrument like XMM-Newton, which helps us to understand stars better.
Hello, my name is Georg Lahmer. I would like to report on my most recent observation with XMM-Newton, and this observation was about a giant dust scattering ring. So the story began with a lucky coincidence. Just after eROSITA started its all-sky survey, while examining the incoming data, I discovered a small, thin ring in the X-ray map of eROSITA. That was in February 2020. What happened here? After some research, we found that about 1 year before the Rosetta observations, at the same spot in the sky, X-ray transient occurred. This transient was from a double star system consisting of a black hole candidate and a normal star. Because matter is falling from the normal star onto the black hole, from time to time very powerful bursts occur on the black hole. And for this system, this happened on the 29th of January 2019. So after a bit more than 1 year, this really large dust scattering ring occurred. So what is a dust scattering ring? The X-rays from the transient take a couple of thousand years to arrive at our Earth or at the satellite recording the transient. But on its way to Earth, the X-ray light also sometimes travels through layers of dust in our Milky Way. And this dust can scatter X-rays, but the scattered X-rays take a small detour. It's not taking the most direct and shortest way to us. And since the outburst is relatively short, only a couple of weeks compared to the travel time, the X-ray light fills a kind of thin sphere of X-ray light. When this thin sphere intersects with a dust layer, the ring in X-ray can be seen. So while this sphere expands, the intersection with the dust layer also expands in diameter, and we see an expanding ring with time. So now XMM-Newton comes into play because we asked for a follow-up observation with XMM. And this happened about 3 weeks after the Rosetta discovery. Since the field of view of XMM has about the size of the full moon, diameter of 30 arc minutes, the scattering ring was much larger than that. We needed 11 pointings with XMM-Newton to cover about half of the ring. The longer exposure time and the higher resolution of XMM allowed us to map the ring in much more detail and measure its diameter and its width much more precisely than with Rosetta. What is scientifically interesting about that? These dust scattering rings allow us relatively accurate determinations of the distance to the object. So this is shown here in this sketch. Again, we see our expanding shell of X-rays intersecting with the dust scattering layer. And we were able to estimate the distance to the layer of dust with the help of the Gaia satellite. And what we also know, of course, is the angular diameter of the dust scattering ring. And we know the time delay, about 1 year, which corresponds to a distance of 390 light years for the detour the light makes. Then with some basic trigonometry, the distance between us and the transient could be calculated. And that was about 11,000 light years with an accuracy of plus minus 10%, which in astronomy is quite a good accuracy for distance measurements. So the light from the transient traveled about 11,000 light years, and some of the photons took a detour of 1 year and formed this beautiful ring. On this sketch of our galaxy, you can see the location of the transient. It is between 2 spiral arms in a relatively lonely environment of our galaxy. So thank you, XMM-Newton, happy birthday, and many more good years.
Hello, my name is Jan Korpas and I'm a PhD student here at the IIP in Potsdam. Today I want to talk about how we use XMM-Newton to study isolated neutron stars. Neutron stars are one of the endpoints of the stellar evolution, more particular the endpoint of the evolution of rather massive stars that combine about 8 to 25 times the mass of our Sun within themselves. Such a star at the end of its evolution will undergo a so-called supernova, where the outer shells will be shed off into space, whereas the remaining core of the star collapses to a rather extreme object, a so-called neutron star. Such a neutron star is, for example, shown here on the right of the slide, and these objects are already kind of extreme, as you can already see just from a few key points like the mass and the physical dimension of such an object. As such, the typical neutron star, so it is assumed, has a diameter of about 25 kilometers and combines about 1.5 or 1.4 times the mass of our Sun. So it's extremely dense, on the same level as an atomic nucleus. At the same time, those stars are also the most magnetic objects in the universe that we can observe, with field strengths that far exceed that what we can hope to achieve in our earthly laboratories. Combining all these, this allows us to study matter under really extreme conditions of high density and high magnetic field strengths, as we cannot reproduce it on Earth. And for that very reason, neutron stars are quite interesting to study. However, if we want to study such a neutron star, we need, of course, to observe it. And since this object is isolated, this already is a bit more tricky, since there are no other objects in the system that could also help us in the study of these objects. So we can only use the emission that the neutron star emits itself, and here we can maybe deviate between two main emission mechanisms. There's first non-thermal emission that is radiated away by particles that are accelerated at the magnetic poles of such a star. You can see this emission here by the focused emission that goes away along the magnetic axis on the image below. And the other emission component in such a neutron star is a thermal emission originating from the surface, where the excess heat that was taken on during the collapse of the star is radiated away. However, due to the fact that oftentimes the spin axis and the magnetic axis are misaligned, the rather focused emission from the non-thermal charged particles leads to a rather characteristic pulsation, which also gave those objects the name pulsar. At the same time, also differently heated regions on the surface that can rotate in and out of view can also invoke modulations in the flux that we can observe or in the brightness of such a star. And as such, generally neutron stars seem to pulsate quite strongly in their brightness. If you have a look at the diagram on the right, you can see how the emission components evolve over the lifetime of a typical neutron star. But what is particularly striking is that both the components are best or pretty well observable in the X-ray regime. This directly indicates why XMM-Newton is such an important instrument for neutron star studies, because it is this wavelength where we really can see the full phenomenology of the population. If we want to study neutron stars with XMM-Newton, we can, for example, take such spectra as you can see here on the right. Such a spectrum can also be modeled by a emission model where we try to understand why the spectrum looks like it actually looks. If we do so quite well, as you can see here on the right, we can directly infer values on the temperature, the radius, the magnetic field strengths, or even the chemical composition of the neutron star atmosphere, which is directly giving insights into the state of the matter of such an object. At the same time, though, the spectrum is not the only thing that XMM-Newton gives us. It also allows for so-called timing studies, where we can use the modulations in the brightness of the neutron star to directly infer the rotational period. Also, the period is not constant, but breaks over time due to the ongoing emission of particles and electromagnetic waves. And as such, if we measure also the breaking rate, we can mark such a neutron star in a diagram on the right, and from that directly infer the age, the magnetic field strengths, or even the neutron star type. So just from those two basic measurements alone, XMM-Newton allows us a variety of insights into the composition and the state of such a neutron star, and this already highlights the importance of XMM-Newton. If you take another look at the image on the right, where you see the currently known neutron star population, you might directly see that some of the neutron star types are more abundant than others. For example, there are many so-called rotation-powered pulsars, which are marked in gray, whereas other types like the so-called X-TINs or the CCOs are rather few in number. This is for the reason that the latter only show thermal emission that is really well detectable at X-ray energies. The rotation-powered pulsars are much better picked up at radio energies, where their pulsation is much easier discovered. This is also a point where XMM-Newton helps us a lot, because over the past 25 years, the database of observations has really grown quite large. And just by chance, it could be that such a rather rare, just thermally emitting neutron star is in the field of view, as you can, for example, see here on the right. There you see that the original target of the XMM observation, which you can see on the left in this image here, just by chance had such a red object at the border of this first observation. Looking again at it with XMM-Newton then showed that was actually a neutron star that was just discovered by chance. As such, XMM-Newton also allows us to increase the population and makes it possible to therefore also study rather rare types of neutron stars that otherwise would go unstudied. Thank you for your attention.
Most of the contributions today deal with dedicated observations that our colleagues have acquired to study their objects of interest. But beyond that, we also make use of the full XMM-Newton observations. To the left, you can see an example of an observation taken in 2003. and is compared to a photo of the moon taken by my colleague Georg Lahmer for a size comparison, because this is about the region of the sky that is covered by a single XMM-Newton observation. And typically, the central object is studied and analyzed by our colleagues to drive their science. But in this moon-sized field of view, we discover between a few tenths up to a few hundreds other sources that emit X-rays. You can see the little dots in different colors in this image to the left, where the color indicates at which X-ray energy the object emits most of its radiation. Exchanging the panel to the right, now to show you what we can find in these images. And one of my main tasks is to develop software that searches for the X-ray emitters in an XMM-Newton observation in an automated way. So we can run the software on all the observations taken so far to find the X-ray emitters in the covered sky regions. If we now observe a sky region several times, look what happens. As in the optical light, the longer you expose, the more you see. Similarly in the X-rays, either by single long observations or, as in this case, by stacking several observations taken over 20 years of XMM-Newton time. This is a total of 31 observations on the same field. And compare the right panel and the number of objects that we detect in a single observation and that we detect in the stack of 31 observations. This is also part of my task to write the software that deals with the overlapping observations and to optimize the source detection in this region to get the best out of the harvest by XMM-Newton. As a side effect of this stacked source detection, we can also gain information on the brightness development of the targets over the years. And here are 4 examples of X-ray sources over a time span of about 20 years. You can see the brightness changes, so we discover brightness variability in the X-rays which we may not have known of before. All this information from the meanwhile 16,000 observations by XMM-Newton are collected in so-called catalogs, which list the objects that our software detects and all their parameters that we can derive, and are made available to the scientists for their discoveries. And the colored bars in this plot indicate how the contents of these catalogs developed over the last more than 20 years, from a small sample of X-ray observations and discoveries up to now several 100,000 X-ray targets in the sky seen by XMM-Newton in those before mentioned 16,000 observations. And this is made available to the scientists so they can find their favorite objects in there and do the exciting science about which you learn in the other contributions today. And if you're interested in learning more about the software and catalog work, then stay tuned for the next Starry Night in the German YouTube channel Urknall, Weltall und das Leben. Thank you.